Hi, I'm Siddharth Krishna, and I'd like to tell you about our work on verifying concurrent search structure templates. A concurrent search structure is any data structure that's indexed by keys and that permits access by multiple threads. Think about implementations of sets or maps, for example. Concurrent search structures like this B-link tree here are widely used in operating systems and databases. But formally verifying these algorithms is hard. Existing proofs are large, complex, and mostly on paper, verified only by hand. In the past, when proofs got really hard, we invented new formal reasoning techniques that allowed our proofs to be more modular. For example, Hoare logic allows us to decompose our proofs based on program structure. So proofs of one method is independent from the proof of another. Separation logic allows us to decompose our proofs based on program state. So the proof of each method only has to reason about the local part of the state that it actually operates on. And techniques like rely guarantee or OEK grease allows our proofs to be thread modular. Despite having all these cool techniques, proving something like the B-link tree is still really hard. The main reason these proofs are complicated is that the concurrency part of the proof, that threads don't mess with each other's results, and the memory safety part of the proof, that threads only access memory they're supposed to, are all intertwined. Fortunately, it turns out that most concurrent search structure algorithms actually reuse a small set of general synchronization techniques, such as the link technique. The link technique's key idea is that when a thread performs an update that might invalidate the operation of concurrent threads, like moving keys from one node to another, then it must leave a link edge that tells the other threads where the keys have gone. So in this B-link tree example, we have a thread here that wants to delete the key 5 from this node. But while the thread is suspended, another thread comes along, notices that the node is full, and splits it, moving half the keys, including 5, to a new node. But since it leaves behind this link edge and the key 4 that tells the blue thread when it wakes up that all keys greater than 4 have been moved to a new node, the blue thread is able to follow the link edge and successfully complete its operation. This linking technique is not specific to B-trees. It can also be used for something completely different, like a hash table. So here we have a hash table where the buckets are basically nodes that contain arrays of keys. And if this array gets full, one thing you could do is to allocate a new bucket node with twice the capacity and move all the keys from the old node to the new node. And once again, as long as you leave a blue link edge telling other threads where the keys have been moved to, this should be safe. So if you look at the proof of the B-link tree and the hash table that we've looked at, hidden among these proofs should be a sort of common proof that this linking technique is correct in the sense of concurrency. And so wouldn't it be great if we could refactor these two proofs and sort of take the common link proof and create a link template proof, one that we verify once and for all, and then instantiate to get the proofs of different data structure implementations that use the link technique, like B-trees or hash tables. So that's the goal of our work, proving these template algorithms correct in terms of their concurrent safety, but that leaves the sort of node level operations in the underlying data structure to be instantiated by concrete implementations. And if we can do this, not only do we get proof reuse in terms of reusing the concurrency proof of linking between different link technique using data structures, but we can also reuse the proof of node level operations for something like the B tree from a B tree that uses the link technique to a B tree that uses another technique like the give up technique. And so what we propose in this work is a new form of proof modularity, one that we call algorithmic modularity, where we can separate the proof along the lines of the algorithms used, one algorithm used for concurrency and the other algorithm used to maintain the underlying structure. And so what we get as a result of this work is proofs that are modular not only in the sense of structure, state, and threads, but as well as this new algorithmic modularity. So what does the template algorithm actually look like? We have on the slide the link template algorithm on the right, and I'm going to step through this algorithm to show you how it works using the B-link example on the left. The core of this algorithm is the search structure op method, which stands for any of the three core search structure operations: insert, member, and delete. So for example, if you wanted to perform a delete operation on a key 6, then omega here would be delete and k would be 6. Search structure op starts off by calling this traverse method, which represents the recursive traversal through the data structure. And what the traversal does at every point, it locks a node that the thread is on, and then calls another method called find next. This method is highlighted in yellow because these are the sort of helper methods that are data structure dependent. So for a B-linked tree, findNext consists of doing a binary search on the keys to find the pointer that the thread should take. So 6 is greater than 0, and so it would take this right pointer here. And then it unlocks the node, moves on to the next pointer, where again it calls findNext. And this time the binary search would reveal that 6 is between 4 and 8. And so it would take this pointer and move down here. Finally, when it reaches a node where findNext tells it that there is no outgoing edge, we then know that 6 must be present, if at all, in this node. And so it can perform the decisive operation, or the actual operation of insertion or deletion, on this node. Once again, this is a helper function that is left to the implementation. Once this decisive operation is done, the thread returns the result. So the key is that this template algorithm, these highlighted helper functions are the sort of holes that must be filled in by a concrete data structure implementation. And our aim is to prove the following specification of this template algorithm. So what you see here is an atomic triple, which intuitively means that search structure op appears to change this concurrent search structure from something that has content C to something that has content C prime, where C and C prime are related by this predicate psi, which is basically the set abstract specification, right? So in the case of delete, C prime should be equal to C minus K, and the result should be true if K was present in the data structure before the deletion. So what this atomic triple means essentially is that search structure op is linearizable, which is the sort of standard correctness criterion for data structures. Now, to do a proof like this, we face a couple of technical challenges. The first one is, how do we specify these helper functions like findNext? Because remember, they should hold for both a B-link implementation and a hash table implementation, indeed any other sensible implementation. So we need to write down the specification in a way that doesn't tie us to a particular data structure implementation. The answer here comes from a paper from 1988, which in some sense was the inspiration to this work. This paper presented an abstract view of concurrent search structures towards the goal of being able to systematically generate new concurrent search structure implementations. And the key idea here was to look at the data structure as an abstract graph, where each edge was labeled with a set of keys called the edge set. And the edge set of an edge is the set of keys for which an operation would traverse that edge. So in the B-link case, the algorithm would send all operations looking for keys between 4 and 8 down this edge. So the edge set of this edge is the range 4, 8. And so with this notion, we can specify findNext as an operation that on a node n, given a key k, it returns some n prime if there is an edge n prime with k in the edge set and none otherwise. The second issue we face is how to specify decisive op. A sort of first attempt to specification might be something that says it takes a node n with content cn and transforms it into a node with content cn prime, such that cn and cn prime are related by psi. However, remember that we need to prove psi for the global contents, c and c prime. Right? Is it true that if we change the local contents of the node, we've also changed the global contents appropriately? Unfortunately, not always. Right? Imagine in this B-link example, a thread was trying to delete 7 and it operated on this node here. Well, then it would say 7 is not present in the data structure, and that would be correct. But if a thread tried to delete, say, 6 and it operated on this node here, it would again return, sorry, I couldn't delete 6, it wasn't in the data structure. But this time it would be incorrect because 6 is actually present in some other node. So there's basically some kind of a side condition that we need to check that tells us when operating on a node is equivalent to operating on an entire structure. And again, we go back to this 1988 paper that gives us the notion of a key set. This is a set of keys that label each node in the data structure. And it's intuitively the set of keys that if they're present somewhere in the data structure, they should be present in this node. So in the B-link case, this leaf here is responsible for all the keys between 4 and 8. And so the key set of this node is the interval 4, 8. And the key idea is that if an operation on some key 7 is performed on a node such that 7 is in that node's key set, then the operation is correct. And the reason this operation was incorrect is because 6 is not in the key set 8 infinity. So we take this idea and we design a new resource algebra, which is essentially a kind of ghost state, something that helps us do the proof but has no bearing on the actual behavior of the implementation. And resource algebra is a kind of ghost state that lets us do local reasoning in the sort of separation logic style. So our resource algebra essentially looks like pairs of sets of keys. where the first part of the pair is the key set and the second part is the contents. So pictorially, you should think of something like this, where each node has a key set and a subset of the key set is the actual contents of the node. And the property of the resource algebra we define is when they compose, all the key sets must be disjoint. And this is actually the case for most concurrent search structure implementations. And what this means is that if we change the contents of a node from some Cn to some Cn prime by, say, inserting or deleting a key k, as long as the key k is in the key set of that node, kn, then we've also performed the insertion or deletion on the global contents from C to C prime. And so this has given us the appropriate side condition to check for when updating a node equals updating the entire structure. And so that's what we amend our spec of decisive op by requiring that k be in the key set of the node n. Unfortunately, we're not quite done, because even though I've written this key set as a function of n, its actual definition in most data structures is a global quantity that depends on other nodes. In the B linked tree case, the key set of a leaf depends on the keys in all the nodes on the path to that leaf. And remember, we want our proofs to be modular also in terms of program state in the separation logic sense. And to solve this problem, we look at another recently proposed framework called the flow framework, which is essentially a way to do local reasoning about global graph quantities in a logic like separation logic. And I don't have time to go into the details, but the key idea is that if your global graph quantity of interest can be expressed as a solution to a fixed point equation that looks like this, then the flow framework lets you talk about this quantity locally, pretend like it's a local quantity of that node, and it gives you a condition under which you can check that modifications to the graph, again locally, preserve this quantity. And we show in our paper how the key set can be defined in terms of another quantity called the inset, which is defined recursively in a fixed point equation that looks like the flow equation. And so we can define a flow that lets us calculate the key set locally on each node. And so we can complete our proof by sort of adding these flow interfaces of each of these nodes, in, to the spec everywhere. And this makes key set ks a sort of truly local function and gives FindNext and decisive op fully local specs. The key of this is that since they operate on locked nodes and the spec is local, the implementation of FindNext and decisive op can prove that they satisfy this specification by purely sequential reasoning. And so we've achieved our aim of separating the concurrency reasoning in this template proof, and we leave all the structural reasoning to the implementation proofs of these helper functions. More details can be found in our paper, and also our proofs are fully available on GitHub. So we've used this technique and verified 3 separate concurrent template algorithms, the link, give up, and lock coupling. These concurrent proofs we did in a separation logic called Iris that is verified by the Coq proof assistant. And we implemented these 3 templates on using different implementations based on B-trees, hash tables, and linked lists. Our implementation proofs, since they are sequential, we used a separation logic tool called Grasshopper that uses SMT solvers and provides more proof automation. So this is another benefit of our work. We could kind of use tools that are better suited for the different parts of the proof. And essentially, we get the proof reuse that we're looking for, but we also get fully mechanized proofs of real-world algorithms. And so a real key benefit of this approach is that when we did the link template proof and the first B-link tree implementation proof, we could then verify our second implementation, the hash table, in just a couple of hours because we reused so much of the original proof. And so here's a summary of what we've done. Verifying concurrent data structures was really hard, but in this work we introduce algorithmic modularity, which is a new form of modularity that helps us decompose these proofs into the sort of concurrency part of the proof and the structural part of the proof. To do this, we had to combine existing frameworks in novel ways and come up with new ideas like the Keyset resource algebra that can potentially be used in proofs of other concurrent search structures. And we obtain smaller, simpler, and more reusable mechanized proofs of real-world data structures like the B-link tree. As a bonus, we've also had to mechanize the flow framework in both Iris and in Grasshopper, and this is something we've also released publicly and might benefit other data structure proofs. So thank you very much, and please reach out to us if you have any other questions.